the recording, right? Feel free to stop me at any time. This was what the session today is about, and what do you call it, on Thursday. All right. So it's here. Okay. Right. So the review, again, just a few slides to cover what we actually spoke about and discussed, and what you will have to do in any past paper questions, and what will come in the exam. All right. So we started off, of course, early on by doing a brief signals and system review. And in that, we did the usual manipulations that we spent some time doing in signals early on, and that are so useful here, right? You know, sliding, shifting around in time, which is something that is useful, as we saw later on in the course, and also reversing signals, which was important for the convolution as well. We also looked at impulse response, and as we saw, the impulse response, first off, if you remember, the impulse response is really the most impactful test you can do on a system because of what it subjects the system to. Luckily, in the discrete time world, the impulse is as simple as putting a signal 1 or a sample 1 into the system and just see what numbers it generates coming out. And then we looked at discrete time convolution, which was, it followed the same process that the continuous time convolution process followed, which was basically a flip and a slide, and then you multiplied and you added. In the continuous time case, the addition was continuous, so a continuous addition is, or a continuous summation is, an integral. In our case, in the discrete time case, it's just discrete values to add up. And we saw that you could do it with the flip and slide method, or you can do it using something called a convolution table. And that also allowed us to do something else, which was deconvolution, right? So I could probably put that here. Let me get a pen, right? So, good. So we could do convolution and right? So remember how this works. You have a set of signals going into a system, right? And then the system gives you, after you, maybe I should put HN here, right? And the output of the system is a series of samples. So samples in the system response is, of course, a set of samples numbers, and you get samples or numbers coming out. All right. So this allows us now to do a couple of manipulations here. Normally I am given this and asked to calculate this. But the reverse can happen. If you want to sort of categorize a system, there are a couple of ways you could do it now. So if I know this and I know this, I could find out what the input was, right? And this is a way that we use in controls and in systems analysis, that you could kind of figure out now, if this was like a sound signal, an audio signal going into something, and you know what the something is and you know what the output is, then you could kind of separate from that what signal was going into it. Okay, it's also a form of coding and decoding, if you like. So we did both of them, and there were a couple of examples that we went through. The midterm has one, the problem set has one, and it's fairly easy. You basically you start off with a convolution table, and you have the yn and the xn, and you just fill in the blanks literally. Okay. As I said, if anybody had a question to ask on that or anything else as we're going through, just just make some sound. I only have one screen, so I can't see our chart at this point. Then we went on to the continuous time Fourier transform. Remember, that's defined in terms of a continuous frequency variable. And we saw that first off, the continuous time transform applied really. It started from the Fourier series and it applied to periodic signals. And then we said, well, okay, how do we make it apply to non-periodic signals? And we did that by stretching the period to be something very large. So the non-periodic signal is really a signal with a huge, technically or mathematically infinite period. In the course of that, this sinc function was reintroduced, the sine x over x type of function. And we met this later on as well. And remember that as x goes to 0, sine x over x, right? Once x is in radians, if x is in radians, as x goes to 0, sine x over x becomes x over x, which is 1, right? And you know that from your AdMaths days and so on, and you could always check it out. So this is why the sinc function at x equal to 0 is 1 and not 0, okay? And then we remember this thing about a spectrum. What was a spectrum? A spectrum is just a display of, or a representation of the frequency content of a signal or a system, okay? Then after that, now we said, okay, well, we're now migrating from the continuous time domain into the discrete time domain. And to do that, we have to go through a process called sampling. And we saw sampling initially was as simple as taking a continuous time signal, and if you multiply it by a series of impulses uniformly spaced in time, right? Then what happened is that because of the properties of the sampling function, the ideal impulse, it picks out the values at these points, right? That was because of this property called the sifting property. And if we only look at these values now, then these, what we have now are samples of the original continuous time signals, okay? Given that you have no idea what is going on in between the samples, all right? So given this, the values here, you do not know anything about these changes of values inside of here, right? Those points are unknown to you, and this is why the speed at which you sample is so important. So we looked at that as ideal sampling. As a consequence of sampling, we saw that there was something in the frequency domain that was created called spectrum replication. Essentially, that if I had something that had a spectrum looking like this before I sampled it, then after I sampled it, right, at some frequency fs, we found that the same spectrum was repeated at fs, at 2fs. Oops, kind of drawn bad, but anyway, right? So you got, when you sample it, you had the original signal, but you had these things going on, and we call these replicants. All right, and that was as a consequence of ideal sampling and the behavior of the impulse. When you take the Fourier transform of this impulse train here, it turned out that you also got a series of impulses in frequency. So that led us to the business about the Nyquist frequency, which is how fast we need to sample to avoid this replication. And we saw that if fs was greater than or equal to twice fh, where fh was this point here, the highest frequency component of the original signal, then you're good to go. If it is less, then you have the signal and the replicants overlapping, and you create something called an alias, IAS. Okay, so to avoid aliasing, you had to observe something called a Nyquist sampling frequency. And basically what that meant is that you needed to know what the highest signal frequency was and sample twice that. After that, now we said, okay, you can't get an ideal sampling because it's impossible to create an impulse. So what we did was then to use a very narrow pulse instead of an impulse. And we saw what that did. If you sample with that now, then on top of the spectrum that you get, real sampling introduces an envelope that has a sinc function shape to it. In other words, you're getting the replications as we go through, but everybody else now has an amplitude envelope that is generated by the sinc function because the Fourier transform of a pulse in time is a sinc function, right? This is the magnitude of h j omega here for the pulse, all right? And that introduced these two concepts for us. And we saw that there were two ways that you could sample. You could sample where the sampling pulse was like this. The sampling pulses were like this in the sampling whole circuit. And this was returning to zero. Or if you made the sampling pulse width, if you may maximize them, then what you basically had was something continuous, almost looking continuous, but you sample here, then you hold, and you sample with this one, and then you hold. And that gave us two versions of the sinc envelope. And you could go back and check and see what the difference was. All right? So now that we had the continuous time transform and the sampling business, we were now able to apply the sampling to the continuous time Fourier transform. And then this gave us something called a discrete time Fourier transform, which was a Fourier transform of a sample signal. And it was defined in terms of a variable called capital omega, which was simply the continuous time domain variable divided by fs. And we saw from then to the rest of our dealings that everything in discrete time domain must have some fs, right? So every single problem that you're dealing with in the discrete time domain, you must have some sampling frequency associated with it. So the DTFT was all well and good, except that we still had integration to perform because we were dealing with continuous time variables. So what we said is that, okay, let's now put some more limits on everybody. We put a limit on the number of samples that we're taking and on the frequency resolution. So instead of omega here, we divvy up omega, and we also the number of samples going inside of here. So we have x n, the number of samples, right, which is going 0 to n minus 1, so a total of n samples here. So we said, okay, let's take omega and divide up omega into the same number, right? So we discretize the number of samples to n, and we chop up the frequency into a number of subdivisions, n subdivisions as well. Doing that now, we created something called the discrete Fourier transform. And this had no integration in it. It had no continuous operations to be done. It was a series of sums. You summed over n, and you summed over the frequency components. So the frequency components, the index was k, where k going from 0 to n minus 1. And the samples were n, where n going from 0 to n minus 1. So it was a double summation over k and over n of the frequency, the sort of frequency core there. right? So this could be done numerically now. We could write a program, two summations are like two nested for loops, and you do that, and you're now able to take a signal, sample it correctly, and then do a Fourier transform on it and see what the spectrum looks like. And then we saw that they could speed it up even more. If n was a power of 2, then there was an even more efficient way of doing this. And it produced a particular version of the DFT called a fast Fourier transform. We looked at one because we were dealing with power of 2, so it's called the Radix 2 FFT. There were other versions, there are other versions that are used around for various applications, and each has its own advantage or disadvantage depending on what you're dealing with. Okay, so once we did that and we saw there were we did the manipulations for that. Out of the fast Fourier transform, we came up with the butterfly operation, right, which is basically that you're taking two samples, you're multiplying, you have something called a twiddle factor here. So you have one sample, you have the other sample, you multiply one by the twiddle factor and you add it up and you get a value, and then you invert the second one and then you add them up and multiply and add again, and so you go on. All right. We saw in some cases, especially with the Radix 2, that it was symmetrical. So you didn't have to do all n calculations. You did up to from 0 to n over 2, and then everything else after that was a mirror image. So one advantage of using a power of 2. After that, now we use that process, the FFT, to conduct some spectrum analysis. And that led us now into talking about things like frequency resolution. The frequency resolution has to do with the number of samples that you have. So if you divide up your frequency domain into n subsets, then this now, each of these is called the bin spacing. And when you put your signal in, and you do an FFT here, it is going to drop the values from the FFT into each of these bins, right? Almost like dealing with buckets of water, right? So you have one bin, two, and so on, right? What happens is that if the output of this doesn't line up with any of the bins, then the value kind of, if it comes inside of here like water in a bucket, you're going to get something called leakage. All right. We saw that you could increase the resolution of the FFT by something called zero padding. So what you can do is to take the original samples here, and you can add zeros to the end up to pad it up to twice the length. And we say normally it wouldn't go past about 4. Right? Usually you pad it up twice in the next to double the size. Okay, up to the next power of 2, typical. We also saw that when you were sampling, that basically what you're doing is starting and stopping sudden. And a sudden start and a sudden stop resulted in high frequency changes because of that sync envelope behavior. It high frequency changes in the signal that you didn't want. So it gave us this concept of a sampling window, which is how do we start and stop sampling without sudden changes? And we looked at a variety of them, the rectangular one, a triangular, triangular, a triangular window, and then even this had its own issues too. So then we started to look at those that were based on cosine functions, right? Based on cosine functions, and we saw the Hamming window. I think Hamming is 2m's, right? And some others. And we use MATLAB to illustrate a whole bunch of them. And basically, the idea behind them is that in the frequency domain, the window has its own spectrum. And what you want is a spectrum that has a big, all of them have lobes in them. You want a large main lobe, right, which is this. And then you want very small or non-existent higher order lobes, right? So you're looking for something that is large, in other words, that has a fairly wide lobe width. And there were a number of them. We basically, as we said, the most commonly used one, because it's easy to manipulate, is a Hamming window. Okay, some brute force instances you may have, you may not have the ability to introduce a window, and you stick with a rectangular window. Just remember that the rectangular window function gives you this sort of behavior and frequency. All right, so we looked at those. Then we looked at something called stationary and non-stationary signals, a very general look at it. But basically, the difference between the two is if the frequency content varies with time. If the frequency content is fairly constant with time, like signals coming from a signal generator, from a power outlet, from a control plant or something like that, then those are stationary and you deal with it normally. If you're dealing with certain other signals like audio, for argument's sake, every time you look at an audio signal, the actual spectrum may shift around. So how we handle that was to take the original signal itself and we split it up into smaller subdivisions. And we do an FFT over these smaller subdivisions. That was called a short time Fourier transform. Essentially, the FFT, but you're using a shorter time window with it. And because it's a time window here, we are open to all the window functions that we just spoke about before. The output of this is an image called a spectrogram that shows you frequency, time, and the amplitude or level of the signal is shown as an image with color. Right? The time and frequency axes could be interchanged, but the idea is that you plot time against frequency and you color code the magnitude. So if you go along, for instance, if you pick a time and you go along this way, at that time you could see how the signal frequency varied. Or if you pick a frequency and you go up in time, you could see across time how they, at that particular frequency component, that single frequency component, how it varied over time. All right, so both can give you snapshots of the signal behavior. And then the last sort of thing we looked at in spectrum analysis was something called power spectral density. When you analyze signals, sometimes the frequency components of the signals are difficult to distinguish from each other. But if you look at the power associated with the signals, then you will find that sometimes things that have a similar amplitude have vastly different powers. And that way you can separate the components more readily. The particular approach we take was to use a version of the power spectral density called the periodogram. There are other versions that we can use, and we didn't touch on that. That's more advanced signal processing and so on. And we looked in both cases, there were two MATLAB functions that you could institute on data to check what the spectrum looks like. All right? Then we led in the other half of the course now. We started to talk about filters. And to do that, we did a brief review of the Z transform. That the Z transform is how we represent discrete time signals. That the discrete time transfer functions or discrete time systems are expressed as something called difference equations. That is the transfer function for a discrete time system, the stability or the location of the poles will have to be inside of something called a unit circle, and that came out of the relationship between the Laplace transform and the Z transform. All right, and we draw a little diagram on the board to show how each of them was. You had the Laplace domain, you had the Z domain, and you had the Fourier domain here, right? there was a relationship between here, right? Remember we said if you let z equal e to the st, that was a relationship between the Laplace and the z domain. The z domain and the Fourier domain was z equal to e to the j omega, and the relationship between these two was s equal e to the j omega here, right? So there's a little bit of a relationship between them. And of course, this relationship is with the dTft, and this relationship here is with the CTFT, okay? This we saw in a little while. We use this to try and help us do some filter designs with something called the bilinear transform as well, okay? So having done that, we looked at transfer function realization, which was basically how to draw out a transfer function, a simple transfer function. Why? Because discrete time systems implement the transfer functions on a sample by sample or a block basis. So something comes in, what happens to it? We drew out the actual data flow. And if you take a difference equation and you draw the data flow straight from the difference equation, you get something called direct form. If you look at the direct form and you realize that A multiplied by B is the same as B multiplied by A for linear time invariant systems, then we could swap the order of processing and save our memory, save half of the memory. And that led us to something called a canonical form. And then if memory is an issue, then basically what you do is that you take a transfer function and you break it up into a number of smaller transfer functions, and you perform the operation in cascade. So this would be H1, H2, H3, and then you have an answer. If you wanted to optimize speed, then you did everything in parallel. So you had H1, H2, H3, right? And then you summed up the answer at the end. Okay, so cascade realization, if you want to optimize memory use, because what you're doing is processing one transfer function at a time and then passing the answer across to another transfer function. So for instance, if you had a sixth order function to realize, you could split up the sixth order function into 3 second order functions. A second order function means you only have to have 2 memory spaces available to perform it. All right. In the case of the parallel realization, you would take the transfer function and you split it up into parallel components. This one is your poles and zeros form. This one is your what do you call it? Where when you break it up into partial fractions. Yeah. And then we started to look now at filters, and we saw that filters, there were 2 types of filters that are of interest to us: finite impulse response filters and infinite response filters. Remember, the question of infinite or finite really has to do with storage, right? Finite or infinite is really about storage. If the system has small storage, then infinite just means how many samples will fill it up. Okay, so the laptop computer that you're on, for all intents and purposes, has huge memory. So infinite for that will be a very large system. Okay, an embedded PIC or Arduino has a fairly small memory space, so infinite might be 100 samples, that kind of thing. So it's relative. In terms of the digital filters, there were 3 categories that we sort of look at. Simple for noise filtering, we looked at something called moving average filters, which basically average values over a period of time. It got rid of sudden changes. It's kind of like how your weighted GPA works, right? You could be going through and you have your 3 or your 4 years in UE. You had one bad course, but you did good in everything else. Because of the moving average process that we do here, you end up having that sudden change where you didn't do as well as you would have liked in a course. That sudden change is smoothed out. So you have a very good result at the end, right? That's a good example of it on non-scientific data, all right? Then we looked at the finite response filters. Those are the type of filters that you want if you're dealing with linear phase. Linear phase means that if I were to plot phase against frequency, that the relationship is a straight line. However, that straight line will look like. Okay? That means that when you send signals into the filter, the relationship between the frequency components does not change. That is important for certain types of processing, like image processing, like audio processing. All right? And the particular type of FIR design we looked at was one that was based on a finite, a Windows-based, right? And the particular window that we commonly use is a Hamming window. All right. So in this case, you see what the ideal response for a system is for the low pass. You have FC, you specify an FS. Okay. But if you were to do the response for that, you know that something that looks like this in frequency will give you something, a response that looks like this in time, an infinite response. So to prevent the response from going on forever, we truncate the response, and that means that we suddenly start and stop the response. So to get around the trouble that causes, we have to use a Hamming window. All right, and we saw that by doing that, we create a filter that has a symmetrical transfer function, and symmetrical transfer functions give us linear phase. And then, now the other kind, if linear phase is not an issue, then we take a different approach and we design some filters, starting off with a known analog filter that is behaving well, and we apply two approaches to it. We can match the time response, in which case we use something called impulse invariant matching. So you take HS, right, which is the transfer function in the continuous time transfer function, right? You get HT, you get HN, you get HZ, right? And then now, hopefully, this is the impulse response in time, in continuous time. This is the impulse response in discrete time. If you match the two of them, because of what the impulse response is supposed to do, the filter's frequency response matches up. We mentioned it doesn't work good for high pass or notch filters or band pass. We didn't cover why, but essentially what happens is that if you try to apply the impulse response to band pass or notch filters and the like, you get a lot of aliasing being created, and you don't get a proper response for that. So the alternative for that is another technique called the bilinear response. And the bilinear response tries to find a relationship between HS and HZ. Okay, and we saw from a couple slides ago that Z equal e to the ST. And we expanded this using our power series expansion, and we came up with something called a bilinear transform, which is bilinear just means two ways. So it's linear in two directions. And using that now, you match the response. It's a frequency response matching. So you're looking at if HS is doing something in frequency, you match what it does, you make your HZ at some frequency. So you pick a frequency for HS, you pick a frequency for HZ, you match the two of them, and because of the mapping, the transfer function mapping, the behavior and frequency in the S domain is supposed to be the same behavior in the Z domain, and they will match exactly at that frequency that you chose. All right? And we saw that in all the cases, you could use, there's a little tool in MATLAB that you could use to double check your answers, something called Filter Designer. And we looked at that. I just put it up. It wasn't, you're not going to be examined on it, but there's like a calculator that is very useful and available for you to use. Okay. And then the last thing we ended up with were a couple of examples. First on digital waveform generation. And we saw the approach for that is that if I have a system, right, and I put an impulse into the system, if the impulse response of this system is such that I get, well, a discrete time version of whatever waveform coming about, I can make that work. So all I needed to do was to get an HZ whose impulse response was a series of samples, whose shape was the waveform I wanted. All right? And we went about, we looked at sine and cosine, and it was simple. To start with that, you look at, you want to generate sine omega t, okay? You match omega. Omega is 2 pi f over fs. You must have a sampling frequency. This is what you're trying to create. And then once you do that, now you look at your Z transform table to see what's the Z transform of this. And then you substitute for the appropriate values of omega inside of it. And then we use that in a particular signaling example that is still used, something called dual tone multi-frequency. Every time you tap a entry on a security system keypad, it's around there. It's even in your cell phone system, although it's suppressed right now, but it's still used as a signaling technique inside of here. Basically, it was a series of a matrix of 7 frequency values, 3 low and 4 high, or 4 low and 3 high. I can't remember. I think it's 4 low and 3 high. So every time you press a digit, it mixed a low and a high frequency and sent it out. And each of the waveforms were digital cosine or sinusoidal generators. And the final thing that we did was a guest lecture by Daniel Ringis, and he showed you a little bit about image processing and how we use some of this stuff inside of here. He mentioned something called a discrete cosine transform, which is like a discrete Fourier transform, except that you're only dealing with the real part. If you remember, anytime you see E to the j omega, that is really cosine plus j sine. The j sine part is the imaginary part. So there's a version of this, the Fourier transform, that only uses the cosine bits. It's a real, so in other words, the answers are all real, and they call that the discrete cosine transform. You will learn that a lot if you ever do things like image processing courses anytime later on. Right, so we did that, and it tied together some of the stuff that we had mentioned before. Okay, so that is a topic content, nothing else. So if you're doing the past papers or the problem sets and you see anything else come up, for instance, there were some questions you might see on JPEG compression, that was part of the guest lecture, but you're not going to be examined on that at all. Okay, we didn't do the technique at all in class. All right, so everybody all right with that? Any questions?
Hi, Sue. I just had one question about the window functions for like the triangle and the Hamming and stuff like that. In one of the past papers, I saw that you gave it to them in a table and then asked for them to apply it. Do we need to learn off the window functions, or is it, if it comes, will it always be that you give us the function?
I always give you it. It will be in the question, or it will be in a table at the end, right? I don't expect you to remember any of them.
Okay, thank you.
Right? Okay. Anything else?
Not from.
Right? Okay, so let me stop sharing this one, and we will move on to the problem sets 3 and 4. Okay? Right, I hope you're all right. By now you should have been tackling those on the past papers and so on. So stop sharing this one. Right, just let me pause the recording a second while I load that. Just give me 2 minutes, okay? Resume recording. Okay, so let's have a look at just the problem sets 3 and 4. And then on Thursday, we will go through any issues people might have had with the past papers. As I keep mentioning, and Daniel would have joked about it, over the years, I've taught the course off and on, and some I've changed things, and sometimes I didn't update the solutions, and sometimes I have the solutions for something that went before that I realized wasn't working, etc., etc. So if something really is off, let me know. Okay. So I'm assuming a big assumption here that you all have had a look at the problem sets 3 and 4. As I said, you should have done that a while ago, and you probably into your past papers long by this. But let's just quickly run through and see if anything happens. One thing I'll mention in this one, courtesy of a question that I got about a couple of weeks ago. Okay, so question 1 was asking you to draw the canonical form or realization of that transfer function inside of here. Remember, the canonical form is the one that only has one set of delays in it. Okay, the direct form is that you implement it as it occurs. The data flow is as it occurs. The standard form is as you're seeing on the screen here. I don't know, let me see if I got point. Right, so the standard form is that expression here. So the direct form, if you draw it out, remember what we kind of do is that we swap the feed forward and the feedback loops for that realization. And if you draw it now, the B coefficients go on the right side and the A coefficients go on the left side. And remember me telling you about this in particular, that there were two ways you could represent the coefficients. When you see the A's appear in the transfer function, you can put the value directly in the table, but then you have to put a minus sign on the summation. Or you can put minus A1, minus A2, etc. in the diagram, and then you use plus signs all the way through. Okay, either way is correct, but you have to remember what you do, how the derivation goes. Okay, so I just put some annotation. So B0 here was 5, B1 is 2. If you put minus A1 inside of here, that will be 0.8, and you have to put, so minus A1 is 0.8, and then you have to put a plus sign inside of here. If you had put minus 0.8 inside of here, then you're going to have to change the summation sign to a negative there. Okay? So there are two ways of doing it. Both are correct, and it just depends on your particular preference. Just don't mix the two of them. Okay? All right. Question 2 there was a diagram on the second page. What type of realization was this, and then what was the transfer function? Well, first off, from the time you see two sets of delays on the feed forward and the feedback diagram, you know that's a direct form realization here. And then to figure out what is happening, what I did is just simply to sort of define some intermediate signals at each of the summing junctions here, right? So W1, W2, 3, 4, okay? And then trace it through. Okay, so W1 coming into W1 would have been B1Z. Okay, coming into W3 would have been B2Z minus 1XZ. That would have been this input, and so you keep going on. So one at a time, you fill it in, and then you add up everything else. Simplify, and then somewhere along the road, you get an answer looking like this. I updated the solution, so you should have the newer solution online. The older solution had, I think, 80 here, and I had 130 below. It's supposed to be plus 130 here. Okay, I have updated this online so that you have the correct version there. All right. Any issue with this? All right. Okay, the canonical form of that, well, the canonical form for it is that what you would do is to swap the A's and the B's. So in other words, the A's would become on the left-hand side, the B's would be on the right-hand side. Just make sure that you deal with this signage as it is. Okay, so for instance, this particular one, they're putting the positive numbers in the amplifier block and they're putting the negative sign on the summation. Okay, so you just watch carefully and replicate this, but what you're doing is to interchange the feed forward and the feedback mechanism. So all of the delays are going to come down the middle. All right, fairly straightforward. Right, question 4. What was it called? What is distortionless transmission? You remember what that is? Anybody? What is distortionless transmission?
When a filter leaves the phase spectrum of a signal unchanged or linearly delays it.
Correct. All right.
Yeah.
So the distortionless is that once you put a signal into any system, it could be well, we sort of generalize and say all systems are really filters of some sort or the other. Once it goes through that, the phase relationship of all the components remain unchanged. Right, so whatever was the relationship between frequency 1 and 2 and 3 and 5 and 9 going in is exactly the same phase relationship coming back out. Okay, and we saw that the way to achieve that was by using something called a finite impulse response system. Those and the symmetrical transfer function give you the finite the finite behavior and the distortionless or constant phase behavior. All right. Question 5, an n-term moving average filter. So the number of terms in a moving average filter is fs over n. So you need the sampling frequency. Oops, wrong way. You need the sampling frequency and you need your whatever is your particular desired frequency for this thing to work. We saw that if I work out this thing and the value for n is bigger than an integer, so it's, let's say in this case we work it out and it wasn't quite an integer, it was 5.1, 5.2, then use 5. If it's 5.6, 5.7, then use 6. All right. Each of them it will have the only way to really know in practice will be to implement both 5 and 6 and see what the response looks like. If it's solving your problem, then you could stick with the lower one. Remember, the more terms that you have to average, the more terms to be averaged by the filter is the more values that the filter has to store before it starts to generate an output. We worked out that, remember, the very first value comes in, and all of the other ones, like in this case, if xn comes in, n minus 1, n minus 2, n minus 3, and n minus 4 don't exist as yet. So it takes 5 cycles before you have the full range of values in it, before you can start averaging properly and get a correct answer coming out. Okay? Having done that, the rest is very straightforward. And if I ask you to plot this, if n equal to 5, remember the number of lobes, you plot up to the sampling frequency, and we went through that. Whatever fs is, if n is even, then you have an even number. You have half of the number. So if n was 4, you would have 2 lobes before fs. If n was 5, you would have 2.5 lobes before fs, and so on. Okay? So it's easy to sketch the response, right? You would see some of the past papers where you're asked to do that, and you label it, make sure and label it carefully, okay? You always have the labeling questions. If it's a 5-mark question to sketch the response, 3 would be for the actual shape of the response, and 2 for labeling everything correct. Yeah? Question 6 now was to use a Hamming window. I asked you to use a 9-point Hamming. window, there was a version of HN here that I told you to remember that is easier to work with. So you do that and you generate the values for HN, WN I give you. Okay, one thing with HN, remember that the sync function at 0, when n is 0, remember, because it's symmetrical. So if it's a 9-point Hamming window, you have to run n from -4 to +4. Okay, sorry, if it's an endpoint FIR filter, you have to run n from -4 to +4. So when you reach n equal to 0, if you plug it in here and you didn't remember, you're going to get the wrong thing. When n equal to 0, right, this sync function is 1. So at n equal to 0, the value of hn is 2fc over f, or 2fc over fs. Okay? The window function is the same thing. And then you find wn by hn, and then you delay it by the appropriate number of terms to make it causal. The second part was a triangular window, and somebody had emailed me, I think it was Chelsea, had emailed me a couple of weeks ago to tell me, well, wait a minute, the notes only have it for n equal to n even. So what to do? Because n is odd here. If you're running from -4 to 4, you have 9 points, right? So I told her, well, you could dig around a little bit. I expected people to go hunting a little bit. I'll put it here. If you went into MATLAB, the same window designer, and you linked it back to the triangle function help, you would get the equations for both n equal to n even and n odd, right? So those have updated the solution, the same thing I just told you. So you have both versions here. All right, so you could, for any L, well, they use L here, or N odd, that is a version, the upper one here is a version to use. And of course, because it's symmetrical, you only have to calculate half. There's always a safe bet with these kind of manipulations. Only calculate half and make the second half the mirror image of the first. You guarantee, because it's symmetrical, you are going to be guaranteed that the response is going to be linear phase, even if the frequency response is off, okay? Because you made an error somewhere. Question 7, well, yeah, you could design it in MATLAB, and if you go into the filter designer and you tell it to import the numerator and denominator, or you enter the values yourself, and then you could tell it to plot. You have to give it a sampling frequency and see if it made any sense. And question 8 was a repeat of 6 as well. All right, 8 and 9. Okay, and here's what some of the results were. Okay, and then, well, so that took care of that basically was it for problem set 3. Any major issues with problem set 3 from anyone?
Hi, sir. Good morning. I just had one quick question about number 3. So I know you said that we could flip the direct form diagram, but was it okay if we used the values we would have gotten in question 2? So like the 15,
Yeah.
50. Okay, cool. No problem.
Right. Yeah, you could use that. Normally, if I were to give you a question like that, I would try not to link the answers too much, so that if you made some errors in the first part, then you won't doubly making a set of errors in the second part, kind of thing. Right? But yeah, that's not a problem.
Okay, no problem.
Right? You got out the triangle window one?
Yes, I did. Thank you.
All right, good. All right. Any other question? Okay, so let me pull up let me see now. Problem set 4. These are just sort of general revision, and then you go to the past papers after. So let me see problem set 4. Where's 4? Right, there we go. Okay. Right, so problem set 4 now. My paper. Right. So this largely had to do with the bilinear transform, the impulse invariant, and so on. Question 1, right? So you're matching the 500 hertz signal, the 500 hertz discrete to 1 radian per second. So the HS on top here, this is just get a little pointer here. Where am I? Yeah, right. This here is a 1 radian per second transfer function, right? Always try to, whenever you see that, if you see any common factors between the numerator and denominator, get rid of them, right? You always like to have this coefficient, oops, you always like to have that coefficient as 1. Okay, so you divide by 2, it wouldn't matter, it will cancel in the end if you were to do the substitution. But basically what you have to do, remember the bilinear transform, you have to calculate a matching coefficient, which is C. And you do that by matching, first off, you calculate what omega is. Omega is 2 pi f over fc over fs, right? So your cutoff frequency is 500 hertz. So omega is this. The matching frequency here is 1 radian per second. So if you substitute inside of here now, you're going to get C is equal to 9.51, and then you substitute that into this equation and simplify. All right, I will send it. What happens if you do this? You're going to get some very strange coefficients. Anybody tried it?
Yes,
Anybody
sir.
tried? What sort of coefficients you got for the numerator?
So in the numerator, when I normalized it, I got like 1.235 by 10 to the minus 14.
Right.
But
Good.
yeah,
Right.
it
Yeah.
was pretty small.
Right. This actually, it is good for maths, but it's a lousy example. You see, what we're trying to do, we're trying to take 1 radian per second, right? We're trying to match 1 radian per second to 500 hertz, but we are using a very, very large sampling frequency relative to everybody, which is 15 kilohertz. When you do that, you're going to get these incredibly small coefficients for HZ, right? Like you said, something like 10 to the 14 and so on. If you try to implement that, you're going to get problems, right? So it's not it was a good bit of algebra, but it's not a very good design, right? Practically, what you would have done for this one, if you were to match 500 hertz, you would probably want FS to be maybe 2 kilohertz or something like that, right? Or worse yet, don't try to match a 500 hertz filter with a 1 radian per second filter. Try to get them a little bit closer, okay? But I'll put up the answer. Yes, the answers are some mighty strange coefficients. And don't be too concerned. I mentioned that already. When you're doing this kind of work, or you're in exam and you're getting some kind of strange numbers coming up at you with 10 to the minus 14 and that kind of thing, don't worry about that. Right? That's all part of the course. Put it on. Yeah? All right. Question 2 was to take this one now and to use the impulse invariant technique. The impulse invariant technique has a couple of steps. You're given HS. From HS, you have to find HT. So you have to find the inverse Laplace transform, which involves breaking it up into partial fractions, looking up in Laplace tables, and then writing out the answer. Then once you have HT, you replace T with N capital T. In this case, the sampling frequency is 100 hertz, so capital T is 0.01. So now wherever you see T here, oh, wrong way. Let me get rid of that. Right, where is, this way. Give me a arrow here. Arrow, good. Right, so wherever you see T, you're going to have to replace it with N capital T, and capital T is 0.01. Right, so this is where you get this coming in, and then you go from that now to the Z transform tables, in the back of the exam, and then you substitute all the way through. And then once you substitute now, you have to simplify the transfer function. So you go from HN to HZ, okay? Substitute and then simplify. You could standardize. Sometimes the question, depending on how complicated the calculation is, I may ask you to standardize, or you can leave it in this form. Just watch the question, okay? Right? If the answer isn't, if anybody did this and getting something radically different, let me know. All right, this was all right?
So I think
Yes, sir.
the provided prototype was a bit different, the HOS. In the problem set, I believe the denominator, the last thing was 8883. But that was it early.
Yes, 8883. Yeah, thanks. Right, so note that up. Right, this here is supposed to be 8, right, 8883. Good, thanks for that one. Right, so the question 3 had to do with high pass filters, and we touched on that. In that case, the factor that we have to deal with is a cotangent, which is 1/tan. So the same approach again, except that you're dealing with cotan instead of, well, minus cotan. There's a minus sign as well to contend with. Remember that. And if you do it and you substitute inside of there, then you get. Do I have the value in here? Look, I have this here again, right? So remember to change that. I probably made my answer might be different because of that, right? So you substitute for FA equal minus C. You calculate the C, put it inside of there, and then simplify. All right. Well, was this correct? C was minus 48 by any chance? One was for Q1 and one was for Q2. I think in one case C was minus 0.52, and the other one C was minus 48. That was correct? All right, let me know if you all do it, and anybody when you're trying it out, let me know. Question 4 had to do with the Windows-based design using a Hamming window, a rectangular window, and then it asks the question if you were to use a Hamming window. A very simple question here. Question 5 had to do with the doing at least an order 10 filter, right? So you take the order, it should be no more than 10, right? So the closest odd order to 10 is 9. So I ran it from -4 to 4, and the calculations are here on the screen. You could always double check. This was the answer I got, right? The realizations, of course, is just to draw the transfer function using your values. So if you're ever given this in the exam and your values are wrong, but the diagram is correct, that is all fine, right? You wouldn't be, you're not penalized twice for anything else. All right, and question 7 and 8 was straight from the notes, right? The last set of slides that we had here. This was a general thing. I commented on this about the impulse invariant design a little while ago, so don't worry about that. You're not going to use it for that anyway, right? But the frequency generator, the tone generators for 7 and 8, that is straight out of the notes. So you could do that. And question 9 wasn't part of our topic. Question 10, well, it was an old question 8, and I just have the comment here. And question 11, actually, I didn't have the solution for that, but that was similar to what we had done in the midterm and before. Okay, so for those of you who still have an issue with that, you look at the number of terms in Yn, right? The number of terms in Yn is one less than the total number of terms of X and H. So you have to use that to calculate the actual number of values that you have to calculate and solve for Xn. All right. Any questions on that? All right. Okay, so now tomorrow, not tomorrow, Thursday, we're going to run through. I put up a whole bunch of problem sets for you all. Sorry, past papers for you all and solutions. As I said, sometimes the solutions might be a little bit odd, but I'm more interested in your approach to it. There's only so many ways I could ask the topics that we covered. So things would be, the way things are asked will be very similar. The order it will appear in the exam will be a little bit different. How I ask you things will vary a little bit, but it's the same topic content. There will be no things on JPEGs. There will be no, what do you call it, on any image sort of processing content or anything like that. Or if you saw any past papers that had anything with audio on it, we didn't do that either. Okay, so on Thursday, same time, 10 to 12 o'clock, work with your problems. If in between you're doing your work on something or something or right and so on, then just send me the solution. I'll scan the solution and I'll run it through and see where the error is. If it's my error, if it's something that you made. Okay. Yeah. So any concerns at this point? Last minute questions? All right. Okay, so, well, hopefully for the rest of the class, I'll give them an indication that the recording for this will be online, so you could go through it again. And similarly for when we meet on Thursday morning, God willing. Okay, so good studying, everyone. All the best, and I will see you all Thursday morning at 10. Please God. Yeah?
Thank you, sir.
All right,
take
no
care, sir.
problem. Take care. All the best.
Yes, sir.